Welcome to the problem-solving section of Chapter 8. We begin with Part 1, and Part 1 will contain problems 1 through 3. Part 2 will contain problems 3 through 6, or excuse me, 4 through 6, and the last part will contain problems 7 through 9. So let's begin with the first problem. Here, the question reads the following. Question 1. 3 identical balls are thrown from the top of a building with identical speeds. The first one is thrown horizontally. Well, let's see. Let's go ahead and just draw a building. And if we place the ball right here, a horizontal velocity would be in this direction here, and let's call that V1. The second one is thrown at some angle above the horizontal, so the second one would be in this direction here, which we'll call V2, at some angle above the horizontal, and we'll allow the horizontal to be the direction V1. And the third one is thrown at some angle below the horizontal. So let's see, how about the third one here, where now V3 is at some angle, let's call it phi, below the horizontal. The question is, how do their speeds and therefore their kinetic energy compare when they reach the ground? And recall that we are told that the 3 are thrown with identical speeds. Now, this is a conservation of energy problem. In other words, since they are all thrown from the same initial position and they all land on the ground, let's say that this is position 0, y equals 0. We'll say that B is the final and A is the initial, which is non-zero, and we can make up any value for the initial position. That the only thing that matters here in terms of conservation of energy is the fact that we have no non-conservative forces, and so any change in the kinetic energy of the ball has to add up to, it has to be matched by the opposite change in the potential energy. In other words, if the kinetic energy of this ball will go up, the potential energy has to go down by exactly the amount so that the sum of what increases, say positive, is matched by what decreases, negative, and so that they sum up to 0. So this is what we're facing here in this problem. And let's view an animation so that we can actually see how this does agree. Okay, let's see if this will be the one. No, not this one. I have to go through all of the ones that I opened up. And I believe that, let's see, let me get my mouse. Oops, I have to get rid of that. Let's see. This is what we want. Okay, so this is the animation where we have a ball, which is shown to us to have an initial speed of 12.5 meters per second, irrespective of the mass, thrown from a height of 25.5 meters. And let's here adjust the angle. Let's take the first case and say that the ball is thrown horizontally. Now what we're going to look for here is what is the final speed and therefore kinetic energy. Note that the ball starts out with some kinetic energy because its initial speed is 12.5 meters per second. It also has potential energy because it is at some height, 25.5 meters above the ground, so its total energy is kinetic plus potential. And the total energy must not change when the ball reaches the ground, since energy is conserved. However, individually, these quantities can change. And in fact, what will happen is that when it first strikes the ground, the kinetic energy will be at the height of the potential, and the potential, will be the value that it initially has plus the value of the potential, so that at ground level where there's no potential energy, we should see that the height of the kinetic energy bar meets the height of the total energy bar. So let's start and launch our projectile. Sure enough, we see that the speed is increasing from the initial value. Potential energy is decreasing, kinetic energy is decreasing until it reaches the ground, just as we predicted. Note that it strikes the ground with 25.61 meters per second. Let's now go 15 degrees above the horizontal. 12.5, same initial speed. And let's see what happens when the projectile reaches the ground. Here, we see potential energy decreasing as kinetic energy increases until you can see once again the two bars, the two columns are at the same height. 25.61 meters per second is the final speed. Let's now go 15 degrees below the horizontal and launch our projectile. And it should be confirmed that 25.61 will be the speed. Now, what will be different between these three, however, is the time that it takes the ball to reach the ground. Of course, when it's launched below the horizontal, the time to reach the ground will be less, since this ball would have had an initial y component of velocity, which was not zero as in the case of the horizontal, and certainly not positive as the case here. So the timing will change, but the speed and therefore the kinetic energy should not change. All right, so now let's go ahead and see if we can go and work out some of these, the argument that we can make. In this case, KB minus KA should equal, in each case, here, before we put equal, let's say plus UB minus UA equals 0. Now UB is equal to, of course, 0 since it's at ground level. So KB minus KA in each case should equal UA. In other words, the potential energy that this should be a B. And KB should actually equal UA plus KA. In other words, the total energy that each of the balls had when they were at position A. Next problem. Here, we're told that a bowling ball of 2 kilograms is suspended from the ceiling of a classroom by a cord of 5-meter length. The ball is released from rest at an angle of 37 degrees with the vertical. We are asked to determine the speed of the ball at the lowest point and the centripetal acceleration. And here, I'm afraid we've lost our picture, so I'm going to try to do the best I can to draw it for you, which is, here is our bowling ball. Here is the vertical, try to get a, it's not easy to get a vertical line, I apologize for that. There's the angle of 37 degrees above. So let's say that this is position A, and that the lowest point when the ball is here, this is position B. The length of the cord is 5 meters, and of course that does not change whether the ball is at A or at B. What does change, however, is the position above the lowest point, which if we say that B is the lowest point, so that YB, we allow that to equal 0, YA at this height here, we have to consider that if this is the hypotenuse of our triangle and this is the position YA, so excuse me, this is the horizontal, then YA is actually equal to, okay, let's see, this is L cosine of 37, and so YA will be equal to L, which is from the, the length of the chord when it's at the lowest position here, L minus L cosine of 37 degrees. In other words, we're trying to determine the height from the position at the lowest point to where it was pulled up and held at that 37-degree angle. So that's the first thing that we need to say about that. The other thing is we need to indicate that we're told it's released from rest, so we know that Ka is equal to 0, but Kb is not equal to 0 because since the ball starts from rest but has some position above the ground, that implies that it will have potential energy UA, and of course gravitational in nature. Since YB is equal to 0, this implies that the gravitational position at B is equal to 0. Therefore, any potential energy at position A should be converted to kinetic energy at position B. So this is where we will begin. There are no non-conservative forces, so we don't have to be concerned about setting the difference between kinetic and potential energy to anything other than 0. No non-conservative. And let's put a sub G here to remind ourselves that we're referring to gravitational potential energy as opposed to spring potential energy. Okay, now Kb minus Ka, which of course we've just said is 0, plus Ub minus UA equals 0, and we've just said that UB is also equal to 0. So KB is equal to UA, and the first part of the problem says what is the speed? Okay, let's see, 1/2 mv sub b squared equals mg y sub a. Notice that the m's cancel, and so v sub b is equal to the square root of 2gya. And this right here, recall that ya, we wrote ya as, let's go ahead and expand on this a little bit. Ya was equal to L minus L cosine of 37 degrees. In other words, the position, vertical position of the ball initially is only with respect to the 0 reference position. In other words, the position where the potential energy is 0. So we've got 2 times 9.8 meters per second squared times 5 minus 5 cosine of 37 degrees, of course the unit being the meter. This gives us a value of V sub B, which is equal to 1.99 meters per second. Now, let's proceed to part B. Part B says when it is at the lowest position, what is the centripetal acceleration of the ball? Well, we know the centripetal acceleration is equal to v squared over r, Here, the v at the lowest position is none other than v sub b, or the distance from the position of the ball to the center of rotation is L, not L minus L cosine 37, because remember that was the position of the ball at point A. When the ball is at point B, it is the radius of rotation is the entire length of the chord. So here, 1.99 meters per second, the whole thing squared, divided by 5 meters, gives us a centripetal acceleration of 0.789 meters per second squared. And if we want to be specific about the direction, centripetal acceleration points upward. Okay, let's proceed to the next problem. Question number 3. Here we are told that there is a bead, the bead of little mass m, 5 kilograms, released from rest at the top of this slide, position A. The slide is frictionless, so that guarantees us that there are going to be no non-conservative forces acting on the system. Energy is conserved. We're asked to determine the speed of the bead at points B and C and the net amount of work done by the force of gravity as the bead goes from A to C. All right, let's begin with the first part. Here, let's determine the speed of the ball or the bead when it's at position B and when it's at position C. Conservation of energy dictates that, let's see, delta K, okay, from B to A, E plus delta U sub G, in other words, the gravitational potential energy B sub A equals 0. In other words, KB minus KA plus UB, of course, gravitational, minus U gravitational A equals 0. Well, let's see. The ball starts from rest, which implies that Ka is equal to 0. And so here, Kb will be equal to U gravitational A, which becomes positive, and we transfer it to the other side, minus U gravitational B, which becomes negative. And this is none other than mg y sub A minus y sub B, and Kb equals 1/2 m v sub B squared. Now, can we not divide out the masses so that in fact the mass of the bead is really unnecessary in this problem? V sub B is equal to, well, let's see, 2g y sub A minus y sub B, and of course we mustn't forget to take the square root. All right, so 2 times 9.8 meters per second squared times 5 minus, I forget exactly what the value of the point B was. Let's have a look. 3.2. Okay, so 5 minus 3.2 should give us 1.8 meters. We're going to take a square root of that, and let me just scroll down. And that should give us a value of V sub B, which is equal to 7.67 meters per second. Now, what about the speed at point C? Well, here again, we can take the difference C to A plus delta U sub G, C to A. And actually, we could have gone B to A, but because K sub A, the kinetic energy at point A is 0, let's save ourselves the hassle of having to work out that term and just use the difference between K sub C and K sub A, again this is 0, plus U sub C minus UA, and gravitational, always make a distinction between spring and gravitational. Let's not forget the spring force is conservative and therefore stores potential energy, which we don't have in this problem. UGA minus UGC, MGYA minus YC equals 1/2 mv sub c squared. M's cancel. V sub c equals 2G YA minus YC square root. Let's plug in our numbers. Square root of 2 times 9.8 meters per second squared. 5 minus, this time, 2 meters, which gives us 3 meters here of difference in vertical position. And so here we get a value of, actually, you know what? 7.67 meters per second was V sub C. I apologize. Let me come back here. If your numbers didn't agree, it was for good reason, since I was looking at the wrong result in my notebook. This is actually 5.94 meters per second. So again, I hope that you catch that, because I put in the wrong number. Anyhow, this is part A of the problem. Part B of the problem asks us to determine, let's extend the page a little further, the net amount of work which is done, let's go to blue ink, the net amount of work which is done by Fg, the force of gravity, in the process of going from YA to YC. Okay? Well, we know that work is equal to Fg, pointing downward in the minus j hat direction, dotted with delta R, which in this case is delta Y, also in the negative j hat direction. So let's see, this is from chapter 7, minus mg of the little bead in the j hat direction. Of course, the minus comes from j hat because it's in the minus j hat direction. Dotted with minus delta y. In, again, the minus comes from the fact that we have minus j hat. And so the work is mg delta y, which should equal, once we plug in our numbers, positive 147 joules of work. And of course it's positive because both the force, gravitational, and the displacement were in the same direction. One other connection that we want to make, and that is with a concept, again from chapter 7, that the net amount of work done by a force equals the change in the kinetic energy of an object. And here the change in kinetic energy would be the difference between the kinetic energy at point C and the kinetic energy at point A. In other words, Kc minus Ka. And if we work out very quickly here, 1/2 mv sub c squared minus 1/2 mv sub a squared, which by the way we know is equal to 0. Plug in our numbers, 1/2, 5 kilograms times 7.67 meters per second squared. Oh, the whole thing squared, sorry, not here. Voila, plus 147 joules. Exactly what we expected and was calculated earlier. Well, this concludes part 1 of chapter 8. Until next time.